Live. Hey everybody, thanks for joining us. Let us know where you're coming from. Give a shout out on the chat. I'm Paul, head of community. I'm excited. We're here with Robert Hodges from CEO of Altinity, and Robert's going to be giving us a DoK Talk, building a Kubernetes platform for trillion row tables, cloud native data at scale. So before I hand things over to Robert, we're just going to do a few community updates, but mostly we'll just let him get going. So let me, oops, sorry, I dumped the gun here. I just want to highlight a couple of things. Recently, we've had a couple DoK mentions in the media, one with Alvaro Hernandez Tortosa. He's featured in the Kubernetes podcast, so you can check that out if you scan the QR code. And Alvaro gives us a little shout out to the DoK community. And then also, as all of you know, Kubernetes turned 10. There's Computer Weekly did a write-up with Google engineer Saad Ali. So yeah, check those out if you want to hear about DoK and where we're headed. And then also the big one, DoK Day back as a co-located event at KubeCon North America in Salt Lake City. That's going to be on November 12th. You can submit your proposals through Sunday, July 14th. So you have a month and 1 day to do that. So make sure you get your talks in. We want to see all of your interesting talks. And then just to let you know, next week we have Tong Lei, Senior DevOps Engineer for Grab, with guest host Brian Waller. He's going to be hosting the town hall next week in place of me. And he's going to be, Tong Lei is going to be talking about Kafka on Kubernetes reloaded for fault tolerance. So that should be a really awesome talk. So hopefully you all can make it. You register, scan the QR code. Of course, you can always just join, the meetup and get those notifications. So you can find us on meetup.com. Lastly, if you just want to find out information about the community, you scan the QR code there. It'll take you to the community page. And then if you're interested in sponsorship of the DoK community, you can scan that QR code. So lots of QR codes. Thanks for bearing with me. I'm going to hand things over to Robert. Robert is, as I said, the CEO of Altinity and one of our DoK ambassadors. You could see Robert presenting at DoK Day. Also, and he was a part of our DoK is a platform on a panel at KubeCon last year. So, all right, take it away, Robert.
All right, thanks. Let's get going here. I just want to confirm, can you see my screen okay?
Yeah.
And audio okay?
Yep, sounds good.
Yeah, and one more procedural question I forgot to ask beforehand, and then we can dive in. Questions, will you be able to see questions from the crowd and feed them to me because I'm not able to see them?
Yeah, sorry. We'll throw them in the chat for you there.
Great, perfect.
Yeah.
And you can just do that as you go along. So hello, everybody. My name is Robert Hodges, and I'm going to be talking about building a Kubernetes platform for trillion row tables. The motto, cloud native data at scale. Our marketing department said we had to say highfalutin stuff like that. What I'm really going to do is tell you what we learned by building a SaaS for running large analytic databases on Kubernetes, as well as helping a bunch of customers do the same thing themselves. So let's go ahead and dive in. I want to expand the introduction slightly from Paul. So as I said, my name's Robert, and as you heard, my day job is I run Altinity. We are an enterprise provider for ClickHouse, which is a very popular analytic database. It has about 31K stars, a huge community now, deployed worldwide in thousands of installations, and runs some really big systems. For example, all the analytics that you get off Cloudflare are served up with ClickHouse. What did we do on ClickHouse as a company? Well, we built a cloud on top of it, but underneath that cloud is actually something called the Altinity Kubernetes operator for ClickHouse. It's one of the most popular database operators out on GitHub, and it basically allows you to manage these complex clusters with a simple piece of YAML. I'll be talking about that during this talk and what we learned. We also do builds of ClickHouse and other kinds of things like backups that are not so relevant to Kubernetes. And speaking of Kubernetes, I started using Kubernetes in 2018. I've actually been working on databases for over 40 years. Kubernetes is kind of new, but I've worked a lot on virtualization. Before that, I had a spell at VMware, so it's a very interesting topic and one I really enjoy working on. And I hope you'll see that joy as we go into this presentation. So let's go ahead and dive in. What's a platform? So this is people talk about them a lot, so I better define what we mean in this particular case, just to be clear. And when we're talking about data or data platforms, I think of it as a custom stack to solve some business problem, like security management, like monitoring. We'll pick the monitoring as the example. But what you can see if you look inside it, and particularly if it's implemented on Kubernetes, which is increasingly where these data stacks are found, is that you'll have your basic cloud resources, compute, storage, and networking. They are sitting underneath Kubernetes, which is orchestrating these and, for example, connecting them to running processes, so on and so forth. You'll have basic services, things like Prometheus to collect metrics, Grafana to show them, Argo CD to help you deploy your applications. You'll then have something managing data. There are multiple types of databases that could be used. We'll focus on ClickHouse, so that's why that occupies the middle. And then you have the apps on top, everything from ingest to visualization. And what you see in these stacks is the closer you get to the top, the more customized it is, because by the time you get to the top, for visualization, for example, that you're showing to users, you're solving a specific problem. At the bottom, of course, it's extremely generic. On Amazon EC2 instances, block storage, S3, so on and so forth. These very generic things that have little or nothing to do with particular applications. So we'll come back to this picture later in the talk, but what I want to do is just talk briefly about how we got involved in platforms ourselves, because since we run a cloud service for Kubernetes, we built one of these platforms. So long before many people were doing it themselves, we were doing it as a service. And what does that platform look like? It's kind of like the bottom half of that picture, the database on down. And we call it Altinity.cloud, and basically it is a platform for running ClickHouse databases. And built on Kubernetes. That was a decision we made relatively early on. And so the way that the system is architected, you will have your database clusters running inside Kubernetes. Each tenant in this particular design gets their own Kubernetes cluster. They may have actually multiple Kubernetes cluster, and they can do whatever they want in there as long as it's running databases. So the databases all run in there, all the metrics collection, dashboards and things like that, those resources are in that Kubernetes cluster. We then have a management plane. It's called the Altinity Cloud Manager, and that's for administrative access to, so that you can make a new cluster, you can schedule backups, you can look at your schema and do the kinds of things that development teams like to do and have, sort of a convenient UI. What's going on in Kubernetes then is that's where and in fact the management plane of course runs in Kubernetes as well, but we won't talk about that. What's going on though around Kubernetes is the control plane and the databases is you have your upstream data sources which are feeding these analytic systems, everything from like applications written in your favorite coding language to event streams like Kafka to S3 compatible storage. And then what's coming out on the other side is something nice that users can see and gain insight on all that data you're collecting. So that's what this platform does. And I'm just giving this as context because it explains a lot of the stuff that we're interested in and where we ended up learning some interesting lessons. So what's inside the platform, I think I've said a lot about that. I won't belabor this, but ClickHouse is basically just a very fast, what we call real-time analytic database. It understands SQL. It can run practically anywhere, literally from a phone. There was actually somebody demonstrated it running in a phone. It certainly runs great on Raspberry Pis, all the way up to huge clusters of hundreds of nodes running in cloud environments. So it's very popular, and it has many of the features that you would expect in an analytic database that include column storage, the ability to parallelize execution very well across nodes, across individual CPUs, and then the ability to scale. And it's open source, which is a great virtue in these systems, as you'll see. So let's look at a particular example of ClickHouse. So what's like what you would do with this. And probably if you come to ClickHouse today, one of the most popular ways that ClickHouse is used is for uh, application monitoring, specifically observability. So for those of you that have applications and are, for example, work in SRE, you'll be familiar with the notion of metrics, logs, and traces. These are sort of standard names now for these different types of information. And these are every large system that's running services generates this kind of information in abundance. So as a result, these everybody is interested in analyzing it, and they build observability systems to do exactly that, or they run in one that somebody has built for them. Here's a typical example of an application monitoring system. It is reading metrics, and the metric data that's coming in is arriving at 100 million records per second in the cluster. That might seem like a lot, but actually for the systems that we deal with, it is not. Um, there are systems that that are far larger. Just some numbers about like sort of size of the size of the records, what the retention is, and then some other requirements that you would have on these systems. The reason I'm setting this up is these are real requirements that or close, sort of the kind of requirements that you would typically expect to find in these systems. And if you run the math, it's interesting just how big these systems get, because this title said trillion row systems. Well, maybe you don't have a system that big and it seems unrealistic that you would really worry about data at that scale. But for this system I'm showing you here, if you run this thing for 365 days or 12 months, it gets pretty big. And this is just a simple calculation from a spreadsheet that's just showing on the red bars are showing how that database, if you start at zero and just begin loading it for a year until sort of the first data begins to age out, you're going to hit about a petabyte of data. So these are 1,000 terabytes here. So you're getting close to a petabyte by the end of the year. The other thing is that the rows, just given the numbers that we provided, assuming 90% compression, well, actually compression isn't relevant here, but that's more relevant for your storage size, but you get a lot of rows of data. In fact, in this case, you will accumulate 30 trillion rows. That's a lot. So this is just an illustration of how big these systems get, to give you a sense of what it is that people are building on Kubernetes, and then we can start to understand why it is that, for example, we as a company are completely fixated on things like storage. We spend a lot of time thinking about how to optimize it. So speaking of storage, let me just dig a little bit more deeply into what's actually happening in ClickHouse. This is not a, there are many databases that serve up analytics. In most of those databases, they're doing fundamentally the same things. So ClickHouse, if you understand how ClickHouse works, it gives you some insight into how these large analytic systems work in general. So with ClickHouse, we'll come in and look at ClickHouse, and you'll start by noting that there's a couple servers here. And so this is a small cluster. These are two servers, and they're replicas of each other. So any table defined on the server on the left will have a copy of it over on the right. You can insert into either one, and the data will be replicated between them. You can also scale this out, have shards. Shards are subsets of your data that you create. ClickHouse is also has a very nice feature called distributed query, where you can just run a query and it will run over all the shards of your data, pick one of the replicas and scan them. It's vectorized, which is to say that it treats the data as arrays, and then breaks them up and sort of processes the arrays in parallel, a piece at a time, using things like SIMD instructions, single instruction, multiple data, and it has the ability to parallelize across many nodes at once. So it's very powerful. Just in terms of storage, which is kind of where I started when I entered this slide, you have caching local to the process. So you're going to have memory. You're also going to have caching on local disk. So for example, if you have attached NVMe SSD, you may use that to cache blocks, so that, for example, blocks that are being read out of the other kinds of storage are cheaper to access and don't require API calls. What are the other kinds of storage? Well, for large amounts of data, at the very least, you'll use block storage like EBS or uh, uh, Google persistent disks. These are basically SANs, so storage area networks, which are connected to your VMs and give you access to high performance storage across a private network. And then finally, another type of storage is very important in analytic systems today is object storage. So we won't talk about that too much in this talk, but that's um, another very, very important consideration in these systems is how to access object storage in a cost-performant way. And just to give you an example of the kinds of issues that you get with object storage, for those of you who use it, you're aware that it's fairly cheap compared to, say, block storage or even locally attached storage, but it has other costs that you don't expect. So, for example, if your access is over distance, like you're pulling data from object storage, it's 10 cents a gig to pull it out into the open internet. If you make a lot of API calls, well, you're charged for those as well. So if you're hitting it constantly, you will run up a big bill. So these are sort of the basics of this architecture. I'm spending some time on it because it sort of gives some context for other things that we'll show you as we move along. We also use Zookeeper, by the way, to preserve consensus. We won't talk much about that. It's just a cluster that sits together and keeps track of information that has to be shared between nodes, like what are the new parts and who has them and what needs to be replicated. So the first problem that we had when we joined this was just figuring out how to manage a database in Kubernetes. And it wasn't even obvious, actually, when we began this really began back in 2019, so now coming up on 5 years. It wasn't really obvious at the time that Kubernetes was the right platform to use. In fact, I was quite against it. Because at VMware had some somewhat unpleasant experiences with data on Kubernetes, and I didn't feel it was mature. We decided to use it anyway. It was a great decision. I was completely wrong, and I'm glad that we made that choice. But the first thing we had to do was we realized this was about the time that operators were the operator model had come out or design pattern had come out a short time before, and so we decided, we've got these complex distributed systems. We're going to need to write an operator to manage it. And the way an operator works is it basically allows you to define new types of resources in Kubernetes and have a manager, if you will, that keeps an eye on those resources and then manages them just like an expert administrator would. So here's a great question here. We'll get to this, issues with operators. So how does it work under the covers? Well, what you do is when you install your operator, it includes a container, which is actually going to execute the operator itself. There may be multiple versions of it, or multiple replicas. You also have what's called a custom resource definition, and that defines the resource. In our case, it's called a ClickHouse installation, and and what it allows you to do is take something complicated like these ClickHouse servers that can run to dozens or even hundreds of nodes and collapse all that information down into, say a couple feet of YAML that describe this cluster and what you want to do with it. So you fill out those clusters. It's just like at that point, it's just like any resource in Kubernetes. If you want to make a new storage class, you fill out a YAML, you apply it with kubectl. If you want to create a ClickHouse cluster, you fill out the YAML, you apply it with kubectl. It comes in, the operator is registered so that it is the manager for that kind of custom resource. And then Kubernetes will just pass the new YAML in, and the operator can have a look at it. And it goes through a process called reconciliation, where it looks at the resources that are out in Kubernetes, compares them to what the resource definition is asking for, and then reconciles them. In other words, make the reality in Kubernetes look like the most recent version of this resource definition that you've received. That's basically how it works. It's an incredibly powerful model. And there's a question here about this. This can be frustrating because the operators may not handle everything. Um, and let's just take one example. Handling failover. Well, part of the reason that so some operators handle this, some don't. As it happens, our operator doesn't explicitly handle that because it turns out that ClickHouse itself has very good failover. It's multi-master. If any, basically, if any one of them dies, you can just go to another one. And ClickHouse is pretty good at selecting others to go to. Backup is another thing that operators should handle for you. Our operator doesn't handle it explicitly, but it's relatively straightforward to configure it to add in backup, and I'll show you how we did that in just a minute. So the first question, in fact, that's relevant to this that you have with an operator, and this has a big impact on how easy they are to use, is how do you even represent ClickHouse or any other database in Kubernetes resources? Because what these custom resources are doing is they're providing a definition, a set of, sort of some set of resources that then get mapped to actual physical infrastructure like processes and storage. So, so here so the choice that we had to make was, do we use stateful sets? And at the time, stateful sets were kind of like the built-in way to handle stateful applications. And they have a couple of nice things, nice features. One is they have predictable names. So when you create one, your applications have a clue that want to talk to it, talk to the pods, have a clue about how those pods are going to be named. I can predict them in advance. The other thing is they know about storage. So they allow you to include templates for persistent volume claims, which will then allow you to connect to particular types of storage, whatever you choose. And if your pod is deleted or if your pod is rescaled, for example, increased in size, the replica will, the operator, will take care of adjusting things, and the stateful set is very convenient here because it just kind of works. So it takes care of the underlying ugliness of gluing storage back onto a pod when it gets restarted in a different place. So it's really good. What are the problems with it? Well, it has a really crappy upgrade model, completely insufficient, actually. It also, in fact, let's look at some of the, like one of the biggest problems we hit. The stateful set kind of assumes you have a bunch of replicas that all look the same. Well, in big systems, that just ain't so. And this is true of most databases. For example, you may have pods in different regions. For high availability. You may have pods of different sizes depending on what they're doing. You may have different versions of the database simultaneously present in a cluster at any time. Stateful sets just can't handle this. There's another more subtle problem, which is a lot of changes, and we'll get into that because it was a big problem for us, is that changes to stateful sets can also cause uncontrollable restarts, because they'll recreate the pod definition. So this is another thing we struggled with. But this asymmetry was an early reason why we said, okay, we can't really use stateful sets. What we're going to do is use a stateful set for each individual server. But as far as the collection of servers, we're going to manage that ourselves. And that's a common decision in operators to use what's there, but kind of supplement it or deal with the things that are bad for databases. So that's essentially the mapping that we ended up with, that we would use a stateful set per server to map resources. And so this is what you'd have the ClickHouse installation, and that would cause the generation of stateful sets, for that, if you have a cluster with 2 replicas, they would include persistent volume claims and pod definitions, and that would end up mapping to, your underlying storage and the pod, which could be one or more processes working together. Speaking of, let's see if I have a slide on this. Yes, this is a good place to talk about this. So one of the things that we did do was that even though we weren't totally we were kind of subverting stateful sets, we still, because we were using them for individual servers, it meant that all the stateful set template syntax could be used, just reused, and that had a couple of benefits. One is it just has a bunch of features. It allows you to allocate storage, for example. It has all the things you need. It allows you to allocate pods. It has all the things that you need to allocate pods. But the bigger advantage is people are used to it. So anybody who's done a deployment and written a deployment knows that there is a pod definition in there, or they've written a used a stateful set. They know that there's a pod definition in there, and they know the syntax. But the other thing is they can add stuff to it. So, for example, you can very easily, and I don't have any show it here, but what you can do is, because you have the pod definition and you can, it's just you have direct access to it and you can control it in our operator in the custom resource. You can do interesting things, like you can add a backup utility. So we write the most this popular external backup for ClickHouse is called ClickHouse Backup, obvious. And it runs in a container, and you can just add it as a container to your pod definition, and voila, you have backups. And we did a few other things like tie it into ClickHouse so that you can invoke it using SQL commands. That was a kind of cool integration, and it basically works. Another thing you can do is you can integrate things like reading environmental variables, which if your operator used some other some other syntax, might not give you access to all the great syntax that ClickHouse, or excuse me, that Kubernetes already gives you to read environmental variables, to get their values from secrets, all that kind of stuff. So by using stateful sets and one per server, all of these benefits, all the good parts of stateful sets became available to us and the people that use the operator. So that's a really important point. And was, I think, a design decision that at the time we spent a lot of time trying to figure out which way to go. This was, after all, a long time ago, and there actually weren't any examples we could look at, but we came to this conclusion. The things that you can't handle, and there's a question here, the upgrading of versions is so painful for most DBs. I had this problem with Mongo. That's absolutely correct. And upgrade is a painful problem. This is something we spent years on. We completely manage that inside the operator. And what the operator does is it does rolling upgrades. All you have to do is change the version of your pod for your database. We'll recognize that, and then we'll kick off a rolling upgrade. And it's pretty smart at this point. It knows how to, for example, it's smart about, if you have a big cluster, which say has a couple dozen like a dozen shards with 2 replicas in each shard, what it'll do is it'll go first and upgrade 1 replica, see how that goes. If that's not so great, then we want to stop. But once you've got one successful one, it then starts to upgrade all of the shards in parallel. And it also knows about how long about quiescing the database in a way that will, taking it out of the load balancer, letting queries drain out, so that you won't bring down applications. And overall, we've been pretty successful at this to make these upgrades effectively transparent to the applications that are using our service, or for people who are building these platforms themselves. This is actually an incredibly hard problem. So, and here we are, we're 5 years in. There are still things that we could do better on rolling upgrade, but overall, we do it. It's 99% transparent to applications. We don't lose data. We actually have in the past. This is another thing. Rolling upgrades are really, really hard to do correctly, because there's corner cases where, for example, if you're adjusting clusters, you're actually changing DNS. DNS names take time to propagate. You can go through states where the cluster becomes confused about who's a member and who's not, or where shards are located. We've spent a lot of time testing this. So these were all things that kind of fell out of this decision to use stateful sets for the lower parts, that things like pods and storage, but then to take care of the higher order stuff within the operator itself. Let's talk about another topic. Separation of storage and compute, and this will pick up the speed here a little bit. Everybody wants to, when they're building large systems, they want to have compute decoupled from storage, because you want to scale them independently. In fact, the most common request that we get for scaling in our cloud service is to add more storage. So, and luckily in the cloud, if you're using block storage, that's pretty easy. You just tell, Oz or GKE, hey, I want this thing bigger. But there's a few details around it to actually getting it to work sufficiently. The other thing in analytic databases, you often want more compute power. Analytics are scan a lot of data, but then they often do relatively expensive operations to do to do histograms, for example. That's a computationally intensive function. So you often will find, hey, the amount of compute I have is not sufficient. Let's scale it up. So in which case we'd want to use a larger VM. And so let me show you some of the things that we developed to help with that. So behind the curtain, here's what's happening in Kubernetes. I think most of you probably know this, but for compute, you have some kind of provisioner. It could be node groups, or you could use, with a cluster autoscaler, you could use Carpenter. For EKS, that's kind of recommended. I personally like it, but the basic idea is you have a provisioner which is out there kind of looking for pod requests and seeing, hey, something is not, I see a pod, it can't be scheduled because it doesn't have resources, I'll go make some. And so what it'll do is create VMs. Same thing with persistent storage. You now have CSI drivers, which are loaded into Kubernetes. They are looking for persistent volume claims that are attached to that reference a particular storage class. That's a definition for what kind of storage you want. And then as Kubernetes, and how this is done sort of deep in the internals of Kubernetes, but basically you ask for storage of a certain type. Kubernetes will make sure it gets handed over to a CSI driver. So that's the storage interface. And in this case for EBS, which is most of my examples here, it'll just go allocate the storage and reflect it in a persistent volume, and off you go. So this is happening behind the scenes. One of the things that we learned for analytic databases is just simplest. You can use like complex bin packing, and have a bunch of processes. For example, a bunch of pods running on the same worker. For us, it just turned out to be way easier because we wanted stable performance. We wanted to understand what was going on, just to map every server direct to a VM. So we will force the pods to specific VMs. We also, because taking advantage of the, sort of the pod, again, we also have syntax that we allow to send them to particular zones, because these are things that you need to be able to control. But it's very simple then to specify the VM you want, and then you'll get it. Volume claim templates. These are the other part again that we inherited from stateful sets. We can select storage class, select the amount of storage. One little thing that we did, which was kind of a difference, was we have a slightly different handling of reclaim policies. This is a special setting, meaning that has special meaning to us, that it says if you delete the cluster, don't take away the persistent volume claims. So if you fat finger cluster deletion, your storage will persist. You actually have to go out with this setting. You actually have to go out and delete the persistent volume claims yourself. But that's better than accidentally deleting a cluster and then realizing, oh shoot, my data's all gone. What you actually do is you say, instead of saying kubectl delete, you say kubectl apply. Take that same YAML, apply it, and what'll happen is it'll come up, find its storage, and you're back in business. So these are, that reclaim policy was actually a learning fairly early on to prevent storage from getting accidentally destroyed. So we map those servers then pretty precisely to, or the ClickHouse servers precisely to compute and storage for each one. So if you run those examples, you'll end up, for example, pods running by themselves on M6I large instances, and then appropriate amounts of storage attached to each one. What's kind of cool too is if you need more compute, if you need more storage, you can go ahead and change the amount and ask for more. If you need more compute, you can, of course, just change the instance size you're using. What happens in that case? Well, this is here you see the example. You just apply this, and we'll go ahead and the operator will see this. It will update the stateful sets, and what will happen is your provisioner, Kubernetes, behind the scenes, will just drop the old VMs and give you new ones. So this is a totally great feature for scaling compute up and down. And of course, the operator, because it knows about rolling upgrades, it will do this in sequence so that you don't you don't run into problems. By the way, one problem that we ran into that if you're building these systems, you might just take a note on, you might ask for these machine types, but that's no guarantee you're going to get them. So one problem that we've had, and we actually ran into this sometimes in Amazon, but more commonly in Google, was we'd ask for a particular machine type, and we would either not get it at all, which is a good thing because the upgrade just fails, but you might get some of them and then hit some resource limit, and then your upgrade would break halfway through. And so one of the things we've taken to doing is actually pre-allocating the VMs so that we know they're available, and then so the workers are available, and then only when we've done that do we proceed with the upgrade. So that's a useful technique, and I think applies in a lot of cases. Another cool thing that we learned, and this comes out of using stateful sets, is they have a number of replicas. One of the things you often want to do in development systems is just turn off the compute. That's usually the most expensive part because you have a lot of compute to do these expensive calculations, but in development systems, you often don't have a lot of data. And so we have a feature that we put in, stop, just a stop property that you add in your resources. And if it says yes, what this will do when you apply it is it will basically just turn off in the stateful set, it'll set the number of replicas to 0, and your compute will be released. And what that means is if your provisioner is set up right, the VMs will be released. So all of a sudden your bill goes way down. Your storage is still kept. You still need to pay for that, but at least you're not paying for compute. And that's an example of what happens. The pods just go away and the storage is still there. When you come back and change that setting to no and apply it, the pods come back. Here's a final trick. So one of the problems with stateful sets is if you make changes to them, they end up rewriting the pods, and it will cause the pods to restart. In general, if you have something that doesn't have state, that's not a problem. But in databases, this is really bad. Databases may take hours to warm up because they have caches. And so this is a problem that some people like one of the Enterprise DB Postgres operator just didn't use stateful sets at all. And this was, I think, one of the reasons. What we discovered was that at some point for some deployments, it's just better if we manage storage directly instead of letting the stateful set do it. So in that case, you have this new property that we added about a year ago where the operator is going to handle the storage provisioning for you. And what this means is if you say have 100 gigs of block storage and you set it to 200, we will go back and upgrade that storage in the background without restarting your pod. For databases, that's a really big deal. And it takes advantage of the fact that cloud systems like EBS, Google Persistent Disk, they can extend even while they're attached to a VM. But Kubernetes kind of puts this roadblock in that it wants to restart the pod. And so we go around it to avoid that. So portability. Kubernetes has a really amazing portability story. I worked on Java for over 20 years, basically from when it came out to in alpha in 1995 through about 2018. And Kubernetes has that same sort of property that you can prepare one of these YAML files, and if you just follow some very basic principles, it will run anywhere from Minikube up to sort of huge managed Kubernetes instances. So platform, because we run a platform and it must run in many places because people have their data in different clouds or even on-prem, we had to think about this. So, and what are the good things about Kubernetes? The containers are very portable. Um, because you're using the cloud APIs, for example, for provisioning VMs, actually porting one of these services from Amazon to GCP is really quick. In our case, when the cloud platform, when we had to port it, we did it in under 2 months, and which is kind of amazing if you think about the differences in the clouds and how complex this is. However, there's stuff that Kubernetes doesn't control, and that's where the headaches are. Probably the biggest single one is networking. So things like VPC endpoints are done in different ways. Ingress configuration, in other words, the load balancers that are the gateway um, to your Kubernetes cluster, they all behave differently. So this was something we struggled with, and that if you move things, you'll struggle with it as well. So one of the ways to solve this is just to take capabilities and push them into Kubernetes itself. Here's an example. When we first started out, we were using in Amazon, we were using the Oz network load balancers, which are good, but we were allocating one per, basically one per cluster. And so that had the impact that, among other things, it cost more. But the other thing was it was really clumsy and difficult to use, because every time you spun up a cluster, you would have to then wait for these load balancers to provision. And because you have to do things like, wait for them to appear in DNS, install certificates, it was really painful. And it meant that bringing up a cluster that would come up in 60 seconds was taking 20 minutes because the load balancer wouldn't come up. So what we did to solve that problem and to make it more portable is we developed what we call the edge proxy, and we would simply have a single load balancer, which could be pretty dumb. All it had to support was to be able to forward our traffic in through the load balancer. And the other thing that we did was this edge proxy knows about SNI, server name indications, which are a way for clients to say, hey, I'm going to this, load balancer IP address, but the server I want to reach has this name. And then what the edge proxy does is it just opens up enough of the TLS traffic that it can, actually it's a TCP, it's an endpoint, a TLS endpoint, but it then can not only route to the server that we're supposed to get to, but the other thing is that we also support TCP IP proxying. So these pods can see the origin node where this traffic is coming from. That is really important because there's a lot of security that is based on knowing where people are coming from. So knowing what their IP addresses are. So this was a pretty powerful feature. It made our deployments simpler because we could just have a dumb load balancer, and as long as it could pass the traffic in, we could then route it. And then, of course, it meant less cloud-specific behavior every time we ported. Let's talk about a last topic, and this is more kind of general and about platforms and how development teams use them. Because again, this is something that wasn't super obvious going in, how people really build platforms and what tools they use. And one of the things that we observed as we worked in our own platform, but more importantly, as we worked with dozens or even hundreds of other customers who are building these things, was that there's a bunch of tools for deploying. You have these stacks, right? They consist of services, and there's a bunch of different ways of deploying them. I've just shown a few popular ones here, but Terraform, for example. Terraform is great for setting up cloud infrastructure. In fact, I would say it's dominant, either Terraform or OpenTofu. On the other hand, people who write applications love Argo CD. It integrates very conveniently with Git. You can, so if you're using a GitOps type of development model, you have everything automated through CI/CD pipelines. It fits in really nicely. And then, of course, there's people like me who are just still writing manifests by hand and applying with kubectl. There's just such a diversity of tools that they are that everybody has different tools. Moreover, and this is I think the more subtle point, is there's different types of knowledge for different parts of the stack. So people who know cloud and Kubernetes administration very well are not necessarily familiar with developer tools. So you'll get, so this has a kind of an interesting impact. And here's an example that, what the impact really is. Technology drives social structure, which you're probably aware of this. Here's a simple example from history. This is a knight invading Normandy around 1060, a Norman knight invading England around 1066. Um, so, but what's maybe not so obvious is, yes, he's a knight galloping around on a horse. It's also a fairly complex weapon system that includes technology, and he's also kind of expensive compared to other things at that time. And having military technology over, historically has actually shaped society. So, for example, the fact that these guys are expensive and took a long time uh, to bring up to speed meant that there were landholding patterns and social organization, things like feudalism, that developed to make it possible to maintain these weapon systems. The point is that your tools and the technology that you're using can have impact about how you organize. So we see this same effect, and this is something that became increasingly apparent as we worked with more and more people, is that people who build platforms tend to split naturally into two groups. There's an application function or team, if you will, and they're at the top of the stack. And so they're doing the customer specific things, the things that are specific to users, and they're using a set of tools that they like. There's a platform team. They are the ones who know how to set up things in the cloud, and they know the tools that make that help or that make that work. We see this amazingly. We see this in big corporations, and it's sort of baked into the bureaucracy. But the interesting thing is, you go to a two-person startup, there'll be one person working on the app and one person on the cloud. And so this is a very durable division of labor. So one of the interesting questions is how to keep these teams from kind of becoming roadblocks to each other. And so one of the things that we learned was that instead of having to, let's take storage, for example, and we will, instead of having to go to the platform and ask for more storage, what we want to do is kind of bring functions into, from the cloud into Kubernetes and kind of make it self-service. So that somebody who knows Kubernetes but not necessarily cloud can actually allocate more storage and to make that happen dynamically. Let me show you something we developed to take advantage of this insight. If you use Amazon, there's GP3 storage is pretty nice, and among other things, it allows you to change your disk throughput as well as your IOPS, and you can dial them up and down when dynamically without and this will happen while your applications are running. That's great because we love doing things without restarts. Here's the problem: you can't do this. You can set up a volume, but if you decide, hey, I got the throughput wrong, I want to go from 500 megabits or megabytes per second up to 1,000, you can't just do that through Kubernetes because it doesn't give you a way yet, in general, of changing these parameters. So what we did was we thought, okay, it should be possible to just go into the persistent volume claim and apply annotations to it that could say, hey, this is what we want, because anybody inside Kubernetes can do that. And so, in fact, there's now an annotation on our systems that we run in our cloud that just says, hey, I want throughput of 1,000. And that's a signal that hey, this should be raised. So who gets that signal? Well, we built a controller. And it's a very simple controller. It's just a shell script. It looks for these changes to PVCs, and then it searches to see if there are these annotations. If it sees them, it just reaches out behind the CSI driver and actually goes and changes the EBS volume itself. Not only that, this is the other thing about talking to clouds is some of these things take a long time. So resizing a volume, for example, or making these, some of these bandwidth changes, they're very slow. And in fact, Amazon only allows you to do one every 6 hours. So you need to track their status. That's another thing this controller does. So this idea is kind of an interesting one, and it's been applied in many different ways. But you basically think of having platform teams and app teams. They have different tools, they have different knowledge, and then you have a way of what you might call shim resources that are these things that allow people who understand Kubernetes to, to make changes that don't require the intervention of the platform team. At the same time, the platform team sets them up, make sure that they're done properly, can ensure that, hey, we're not violating security. So this notion of shims is a very, very powerful idea. At the time we did this, we were not really aware of the fact that there were systems like Crossplane that do this, but this is a very this is a very durable idea, and I think a very interesting one as you're building these platforms, to think about allowing the app teams to manage things themselves through these resources that then can reach out and change the outside environment. So we learned much more stuff than this, but I think an interesting question is then what's in the future, because Kubernetes has, once you get over, I think you can see we spent a lot of time thinking about how to manage storage, particularly block storage, because most of the existing systems when we started, in the cloud, we're using that. Some of them were using, we use NVMe SSD as well, but that's not as versatile because you can't scale the compute around it as easily. So what's the future? Well, the analytics space has some really interesting changes going on. And I think one way I think of it is that what is happening now is that we have such a diversity of storage, plus we have these vastly different prices for using both storage and compute. We have huge data sets. People are trying to figure out how to integrate with AI, and then we have some new technologies, specifically open file and table formats. So data lakes, for example, have pretty much settled on Parquet as a way of representing very large amounts of data. That's a file type. There's a table organization called Iceberg. As an example of the different costs, if you run a query in something like Snowflake, which is a SaaS, really excellent database, that the compute that you get charged by Snowflake can be up to 60 times the price of the same compute down, if you get it from a cheap hosting provider like Hetzner. So these are, and then of course the capabilities of storage itself are just vastly, vastly different. The number of IOPS, the speed at which you can get things, latency, time to first block, stuff like that. So many people who are dealing with these large data sets are starting to realize we need to build something ourselves. And the cool thing about Kubernetes, and I think the thing that we have proved to ourselves and are now working on sharing with our customers and the rest of the world, is that you can now build data warehouses or analytic databases, which are built up from open source components like ClickHouse, like the operator that we built, like Grafana, like Prometheus. You can build them out of open source components. That's not new. But what's interesting is you can also now spread them out using Kubernetes. Think about them being built on these pools of compute, which are Kubernetes cluster, as well as all these different types of storage. So for example, and this picture I'm showing you right here is actually the design of a security information and event management system. And the way that it works is they collect a lot of source data in local regions, but source data and they put it on S3. S3 is really expensive to read across regions. It's 2 cents a gig. So if you want to scan data, do you want to, if you want to scan data, you're going to be, if you do it from another region, it's going to be really expensive and kind of slow. At the same time, you can't just do everything locally because your applications want to have a single point to go to ask questions about what's happening across all environments. So what you can do with Kubernetes is you can run a Kubernetes cluster that hosts your central data warehouse, and then it has, in ClickHouse we have what are called distributed tables. They can then issue queries down to other ClickHouse servers, which are running in each region, so they are close to the object storage. They can read it for zero cost. They're close to the block storage, which only works within a single availability zone. And what you get is kind of a best of both worlds. So you're pushing most of the compute and into the regions where it can run at zero cost because relatively low cost for the access to the storage. But at the same time, you're able to have compute in other places that gives you, for example, where it's convenient for users. So this moving of compute, using different types of storage and then having compute, conveniently located to them is a very, very powerful technique and one that's sort of time honored in distributed data, and one that Kubernetes enables. So that's kind of it. So we are working on that now. As I say, this is a real system that's running today. And we have many others like this. So this is a really exciting area, and one where we see Kubernetes having a big, big role to play. So more information. Here you go. So you can come visit us. We have a blog. We have a YouTube channel. We have code repos that include many of the things I've described here. And of course, this ClickHouse. Go check it out. And that's it. So you can get hold of me on LinkedIn or at this email address here. Paul, I'll give you guys a copy of the slides, and
Awesome.
And we're hiring. Come visit us.
Awesome. Well, thanks so much, Robert. We do have a question here from Hamza. It says, do operators provide an easy migration process to ClickHouse Cloud?
Yeah, it depends on which cloud you're talking about. So, because we have a cloud. So, if you mean the ClickHouse Incorporated cloud, no, there's not really a connection to it. But what it does do, if you use the operator, what you can do is you can for example, you can run a cluster in our cloud, and then we even have an export feature, which will give you the operator definition that we're using, and you can take it out, and you can now make the same cluster in your own Kubernetes. And in fact, we have a bunch of customers that do that. They use us to run the production clusters because we monitor those, and we have support people watching them. But then they run their own development clusters at home, even on like on a laptop. So in that sense, what we're trying to do here is to provide a common stack that you're using the same operator, the same database, the same features for backup, monitoring, so on and so forth. You can run them anywhere you want. We have them in our cloud, but you can run the exact same features elsewhere. And we even have a feature where you can set up your own Kubernetes cluster, or just give us access to your VPC. We will set up all of this stuff, the Kubernetes cluster, and all of the services that run on it in your own environment. And so you have direct control of it. And if you decide to migrate away from us, you just unplug. You just take away the management connection.
Cool,
so I hope
thanks.
that answered the question.
Yeah, I have this maybe is a loaded question or too general, but we're celebrating the 10th year of Kubernetes. What are the advancements or changes to Kubernetes that made a data platform like you described possible that maybe wouldn't have been possible at the beginning of Kubernetes?
Operators. I think that's the single biggest thing. But what's cool, you had one of the references you had was to storage. Storage has just gotten vastly better. Originally when ClickHouse was developed, it really didn't have much support. I don't think it even had support for storage. It was just stateless apps, but the storage management is good. And then the fact you have operators is great. Looking forward, because if you have a follow-on question, what would I like changed? I would like to see more respect in Kubernetes for the fact that some processes just don't like to restart. And that Kubernetes has this notion that, it's the pets, not cattle. Cattle, not pets. Sorry. These things are all just a bunch of pods. If one gets into trouble, you kill it. Well, look, if that thing took 2 hours to spin up just to start accepting connections because it was opening a bunch of indexes and preparing memory caches before it really runs right, you really don't want to restart that unless you have to. In that case, it's kind of a pet and you want to be nice to it. So Kubernetes, there's some ways I think that Kubernetes could allow people, for example, to scale resources, and some of this stuff is coming. Add more memory to a pod for example, without restarting it. That is a really that's the kind of thing that we're looking for.
Yeah, well, luckily there's a lot of smart people working
Yeah.
on Kubernetes all the time, as we've seen. I guess there's one last comment here. I think we can put in just so from Brendan Cox. Just wanted to say after using other operators, the design choices that have gone into the ClickHouse operator have been top notch. No manually fixing stuck stateful sets.
Brandon, I've got your email address. Say, yeah, the check's already on the way. No, thank you very much. No, it's serious. You know what they were? There were some really good choices, and I want to be completely upfront. Most of them were not mine. In fact, I even argued against some of them. So yeah, there've been some really good choices, and then on top of that, I think the key thing here is we run these things. We run hundreds of clusters at this point, and so a lot of the stuff that if we didn't have the right design choice at the beginning, we've iterated and improved over time just through bumping into different things to make the operator work better. It's a great piece of software.
Awesome. Well, with that, I think we're at the top of the hour. But yeah, I want to say a special thank you, Robert, for giving us this talk. I think it's super informative, and we will be hopefully seeing you soon. Hope maybe at KubeCon in the fall.
Yeah, thanks. And everybody, come join if you're not in part of Data on Kubernetes. Come join us. It's a really great field, and we welcome new people.
Yeah, great. All right. Well, thanks everybody. Have a good day. We'll see you. Hopefully, see you
All
next
right.
week, next Thursday for our town hall. All right.
All right. Bye bye.
Bye.